So, okay, I restarted the machine and So you are looking at the signals lab, and I'm going to give you some hints about all right, so we were looking at signals, and the signals are a mechanism. It's a small message that notifies the process that, so I want to refresh your memory. So if you think about when something goes wrong in the CPU, in hardware, there is a divide by zero exception, an exception handler runs, or you're trying to access an invalid memory address because your pointer arithmetic is somehow flawed. The CPU goes to an exception handler and starts running an exception handler that does some cleanup. At this point, there is no way for the user process to know what is going on. And signals are a way for the kernel to tell the user process, hey, you did something wrong, and here is a signal for you. The other reason signals are useful is for two processes to communicate with each other. And so this is a lab where you are trying to write signal handlers, and you are trying to set up a communication channel between processes. There are some concurrency bugs. Things are happening at the same time, races. This is already a sort of your first introduction to concurrency. So I'm not going to give you any solutions, but I'm going to talk about where I left. So if you're already doing the lab, this will help you. So the important thing is that signals are, when you handle signals, when you write signal handlers, they execute in your user code. You can think of it as a concurrent control flow. So your user program, your main code is running, and then a signal arrives, and the kernel has to notify the process and start running the signal handler. The problem here is you may have variables that are shared between the main program and the signal handler. There must be a way for the user process to block signals for a while, so it can do some critical things. For instance, adding something to a linked list or stuff like that. So we have explicit mechanisms for blocking. For user processes have explicit ways to block signals for a while, to tell the kernel, hey, look, I know there might be signals, but hold on for a second, okay? Now, there is an implicit blocking mechanism. When a signal handler is running, when the kernel delivers a signal to a user process and a signal handler is running, if there are more signals of the same type, the kernel does not notify the user process. They are blocked and they are dropped. Okay. A pending signal is received at most once. So kernel maintains pending and blocked bit vectors in the context of each process. So these are like, there is one bit for each signal type. So if there are 32 signals in a particular system, there are 32 bits in a pending bit vector and a blocked bit vector. So the pending bit vector informs, in fact, the kernel keeps track of which signals are pending, which signals do I need to deliver to the user process. And the blocked bit vector keeps information about signals that the user process has blocked. The user process tells the kernel, look, I don't want to receive signals of this type. So there are these two bit vectors in the kernel, and we can manipulate these bit vectors using sigproc mask function. And these bit vectors, we also call them signal mask. So we can create these masks, and we have a function and there are some helper functions that help us set up these bit vectors or masks. Are you for some strange reason, it started working. Now, the problem is I have no clue why is it working. And this is a bigger problem than it not working, because there's another lecture on Thursday. So it says the air media certificate is not valid because I use the wireless presenter. HDMI does not work for me. So what happens now? All right, so let me introduce a process group. So each process belongs to a process group, and a process group is typically taken as the PID of the parent process. So here I have a foreground job running in my shell. At this point, you know what a shell is. You have a foreground job that creates two child processes, and they both are in process group 20. So this is just something that will be useful in a bit. Each process belongs to a process group. And we can get the group and we can set the group using utility functions. Here, when we say, so there is a kill utility. In the shell provides a kill utility that you can use to send signals to processes and process groups. So here I'm sending the signal 9 using the kill utility. Depending on how your shell is set up, you can just type kill, or you need to type bin kill, /bin/kill. Now this will become clear when we talk about file systems and storage and all that, but for now, just. And I'm sending the signal -9, which the English name for this signal is say kill, and it kills the process 24818. If I say negative -24817, it will kill every process in the process group 24817. So there are process groups. You can send a signal to a process group, or you can send a signal to a process. So when you type Control-C, the signal that is sent to every foreground job is SIGINT. Interrupt, INT is for interrupt. If you type Control-Z, you send the signal SIG stop, suspend, suspend or stop. Now the default action for every signal that you send, there is an associated default action with that signal. So a default action with SIGINT is to terminate each process, and the default action for associated with SIG-STP is to suspend each process. Suspension means that the process is not running, but it hasn't terminated. If we send it a special signal, SIG continue, it will start running again. So there is a way to suspend a process. This is how we can send signals from the keyboard to jobs running in the shell in the foreground. Okay. Okay, so I don't want to go through this, but if you need, as the lab handout says, what PS means, what PS prints, you need to do manual You need to look at the manual entry for man PS. Okay, so you can send signals to another process with the kill function. So here the parent is forking a number of children. These children are just executing in a while loop. Sorry. Yes. And here, the parent is using the kill function to send a sig interrupt signal to the child processes. Now, unfortunately, okay, this is one of your exercises. So you can use the kill system call, specify the process ID, and send a specific signal. So here, these signals will actually terminate the children. So there's an important thing. The kernel needs to do some work to deliver a signal to a user process. Now, how does this happen? The user code here, once again, this is user code, this is kernel code, this is user code. So when user code is running, the kernel doesn't do anything special to notify the program of any signal. Whenever there is a system call and the kernel is returning from a system call or returning from an exception handler or from a context switch, at that point, it checks to see if there are any pending signals. It checks the bit vector, the pending bit vector, to see if there are any signals to deliver to the process. So it computes P and B variable pending signals and not blocked. So the signals are pending. There's a bit in the bit vector, the pending bit vector, that says the signal of this type is pending, and it is not blocked by the user process. If this is the case, well, if this is not the case, the kernel does nothing. It returns control to the user process, and the user process executes the next instruction. If there is a pending signal and it is not blocked, then the kernel chooses one of the signals, the least non-zero bit in this bit vector, and forces P process to receive the signal. So you have some intuition right now already what it means to receive a signal. There is typically, you install a signal handler, and the kernel knows that there is a signal handler for a specific signal, and it starts running that signal handler. All right. And you repeat for all non-zero bits in the pending and not blocked. This means pending and not blocked. So the reason to do that is partly for efficiency reasons, because you don't want to check all the time by going inside the kernel code that there is a pending signal or no. Whenever the kernel is returning from a context switch, so here it is returning from a context switch. It is saving the context of process B and giving control to process A, restoring its context and registers and everything the way we discussed. And the one thing it does, hey, let me also check if there are any pending signals. Okay, each type of signal has a default action, but you can override that default action by installing a signal handler, which you are doing in the labs. So signal handler, the type definition of signal handler is a function pointer. It takes an integer and it's a void. It doesn't return anything. And then we use this type to install a signal handler. We write the handler, we write the function, which takes an int, returns nothing, and we call signal with the signal number that we are installing the handler for and what to do. Okay, so this is called installing the handler, catching or handling the signal. And when the handler executes, the return statement passes the control back to the actual function. So here's an example of a signal handler. So here, the process, the user process, the main program here is installing a signal. It's telling the kernel, whenever there is a signal sigint for me, run this handler. So when the kernel is returning from a system call or an exception handler or from a context switch, if it sees a signal of type sigint for this program, for this process, it will execute this handler. And this is what we call receiving the signal. The signal is delivered. Now, when this handler is running, if there are more signals of type sigint, they are implicitly blocked by the kernel. All right, they are not delivered. This is important for you to do some of the exercises, this property. Signal handler is not a separate process. It is a concurrent flow, but it is not a separate process. So process A, let's do this. Process A and process B, are they concurrent or no? Process A and process B are concurrent, even though they don't execute simultaneously at the same time, because probably there's only one CPU in this graph. And so either process A runs or process B runs. But they are both, they haven't terminated. Process A hasn't terminated after process B has begun execution. They are both still overlapping. Their execution is overlapping in time here. Okay. The handler belongs to process A. So either the main program is running or the handler is running, but not both at the same time. And this is already an issue of concurrency. This is concurrency. Your handler might do something that is then visible to the main program. You might have a global variable. So both need to synchronize, both need to know what is happening to those global variables. So imagine process A is running. And at some point, something happens. There is an interrupt. The kernel decides based on a timer chip. There's a timer chip that interrupts the CPU, telling it that a certain amount of time has passed. And corresponding to that timer interrupt, the kernel starts executing an interrupt handler installed somewhere, the way we looked at in the first few lectures. There's a jump table, the CPU jumps to that. It schedules out process A. This one is switched out of the system. Its context is saved somewhere. And this one is brought back into, this one starts running, process B starts running on the CPU. So this is context switch. Now, when process B is running, there is again a context switch. This time, the kernel does something on behalf of process B, saves its state and other things, and then it does something on behalf of process A, for instance, restoring its state. Now, this distinction between user code and kernel code, why we switch from user to kernel code, what are the things we can do in user mode What are the things we can do in kernel mode? I'm emphasizing for a reason, because this is going to help you in the labs in the future. Now, when the kernel is returning control to process A, at this point, it computes that this P and B bit vector, which signals are pending and not blocked. And for each signal that is pending and not blocked, it starts executing those signal handlers if they are installed. If they are not installed, it does something. It takes a default action. What, in your opinion, is the default action for segmentation fault, a signal that notifies the user process of a segmentation fault? Terminate, right? You've been getting segmentation faults in the lab, right? You can cheat and you can write a handler for that signal, and then you won't have a segmentation fault. But don't do that. This is wrong. You have a problem in the program somewhere. You're accessing an invalid memory. You're doing an invalid memory access. Don't mask it. Don't hide it by writing a signal handler that prints something. Hey, everything is okay. Because when you go back to the main program, you will crash anyway, most likely. So don't write signal handlers for things, to hide the bug or something. Okay, so the important thing here is that the signal handler is running in user code. So even though the kernel is, we notify the kernel there's a signal handler and it's executing, but it is running in user mode. The bit and the control register in the CPU that informs us, is it user mode or kernel mode? That bit is in user mode. We don't want programmers to write signal handlers that do something really nasty. So a signal handler can actually be interrupted by other handlers. So you might be executing code for a signal handler, and you might get another signal. Now, if you are executing a signal handler and you don't want this situation where you are interrupted by another signal, what can you do? You can block all signals. You can explicitly block all signals. So blocking and unblocking signals, implicit blocking, whenever the user code is running a signal handler, the kernel by default blocks all signals of the same type for which the signal handler is running. We can explicitly block signals using the cs.proc mask function. And there's a bunch of utility functions that actually help set up the mask. Okay, so the sig.empty set function. So you create a mask of this type. This is a bit vector, and you pass a pointer, the address of this, sorry, not the pointer, the address of the mask, this variable, to different functions. Okay, so sig.empty set initializes the mask, and it excludes all signals from the set that are defined by the system. So no signal will be blocked if this is the mask. You can add a signal to the mask. If you're going to block a signal, you first add it to the mask by doing this: sig add set, the address of the mask and the signal that you want to mask or block. And then you call this function cs.proc mask. And this will tell the kernel that you want to block signals that are defined in this mask. And the previous mask is stored in the previous mask variable. So the typical flow is that you create two variables, mask and previous mask, right? You initialize the mask, you add a bunch of signals to the mask, and then you associate an action with those signals. So here I'm saying sig block. You can also say sig unblock. That will unblock the signals that are added to the set. So this sig proc mask will block sig int because here we add sig int to this set. And it's useful to grab the previous mask. So if you want to unblock the signals, you can apply that mask. And the function for that is you can do that with sig proc mask. And you can use this option, sig set mask, and provide the previous mask. Okay, so you block a signal, you block sig int, you provide the mask that you created to block sig int, you store the previous blocked set or previous mask in a different variable. And then once you are done with your work, once you no longer want to block sig int, you can apply the previous mask by using sig set mask. So this is how you block and unblock certain signals. You keep two masks, one where you add signals to the set. You call sig proc mask and you store the previous mask, which is the last argument of sig proc mask, and then you set mask, same function, and this will restore the previous block set, unblocking sig int. So this blocking signals and unblocking signals will be really handy throughout. We will have issues of concurrency. We don't want certain signals to start executing signal handlers while we are doing something really, really critical, like doing something with a data structure. And we will want to block all the signals while we do all that. Okay, there's a bunch of safe signal handling. Because of the concurrent flow, because the signal handler and the main program share variables and they run concurrently, we need to be careful when we write signal handlers. So there are some guidelines. Don't write your entire program in a signal handler. Keep it as simple as possible. Okay, this will become clear over time. Async signal save functions. Functions that are tolerant to asynchronous signals. Functions that, if run asynchronously, don't mess up the state of the system. One way to look at, so all these signals are not safe. One way to look at it is, if your function only creates variables on the stack, it is probably safe. Now, there's a bunch of other properties that we will learn over the course of the semester, but this is one way, one property. What is the problem if you have variables outside the stack? If you have a variable with a static storage duration, what is the problem? You don't know whether it's triggered and you don't know it will be there. All right, so in lab 3, you looked at the storage duration of variables, right? So what is static? Static variables are stored where? In the global segment. And static variable, if you declare a static variable inside a function, what happens? what am I doing? Let's say you have a function static int I equals 0, I11, and let's say I make two calls to this function, and I printf I. What will I be after the second call to function? Static, when you declare a variable as static, it becomes a global variable. The storage duration, the duration, the lifetime, how long a variable lives, how long a variable on the stack lives. What is the lifetime of a variable on the stack? A function call, right? After the function returns, the variable is automatically dead. That stack -8 reclaimed. Static variables have a lifetime that spans the entire duration of the program. So we say that a function that uses static variables is not, this is a terminology, reentrant. A reentrant function is that does not have any static variables, that only creates variables on the stack space. So these variables, these functions that do not use static variables are safe to call in signal handlers because they don't have any state across two calls. If you have a state, then different things can happen. If there's another signal, then if that handler calls the same function, you can end up with different problems. So save and restore error number or entry and exit. The main program might be using error number for a particular reason. And if your signal handler calls a function that changes error number and you return to the main program, then you lost the error number that the main program wants to use. So save and restore error number. This one is important. If you have shared data structures that different signal handlers want to use, or the main program wants to use, you need to block all signals while you're executing the signal handler. And this is a source of many problems. If you don't block signals in your handler, then you might end up with possible corruption. If there's another signal and you're interrupted. Okay. I want to do this quickly, but this will become more clear when we talk about memory systems. Volatile, the compiler, you're already seeing in your labs that the compiler is trying to do smart things that is bothering you, right? It is trying to optimize away while one, right? One thing the compiler can do is, in the main program, in the main code, if you only read a variable, let's say you have a variable flag, and at different points in the program, you're only reading the variable. The compiler can put the variable in the register file and always use the register to access the variable. So if signal handler writes the same variable flag somewhere in memory, then the main program will never see that write, because the compiler did the optimization of always reading the register, reading the variable from the register. And you can prevent that with the volatile keyword. The volatile keyword in C tells the compiler to always read the variable from memory, to always read the most up-to-date value of a specific variable from memory. The signal handler could do a write and do a store instruction, move the variable to a memory location, while the compiler will keep reading the variable from the main program will keep reading the variable from the register file. Okay, there is something called atomicity. Not all instructions execute atomically. If you do a, if you say flag equals flag plus 10 in your signal handler, even if you say flag equals 10, the hardware may execute this instruction in multiple steps. It is not atomic. It is not guaranteed to be atomic. This could be due to several reasons. You might be on a 32-bit architecture, and you have a 64-bit variable, and somehow the CPU is using 2 registers to give you the illusion that you have a 64-bit variable. Or there could be many other reasons why a single instruction may be interrupted due to some reason. And to prevent that, you can use the SIG atomic type in C. So flags declared this way does not need to be protected like other globals. So you can use this atomic type, SIG atomic T, to make sure that all instructions, all updates to certain variables happen atomically. So this is only applicable to a single read or a single write. Why is flag plus plus different? Isn't flag plus plus a single instruction? Right, yes? Right. So what it's really doing is what? Flag equals so it's reading the flag and then doing an add and then doing a write, probably. So the SIG atomic type is only useful when you have a single read or a single write of this form. Okay, so I want to say that these two will become clear over the course of the semester, but I just wanted to throw it along because it's there. As much as you can follow these guidelines when you write signal handlers, it will help you. And the list of functions that are not safe to call in signal handler, we will give you a table whenever, when the time comes. So printf is not safe to call from a signal handler, and the cs.app.h that we have given you. Okay, so I want to say that it will be good if you can just quickly skim through cs.app.h and cs.app.c. We will be using it in the future as well. It has some safe functions to call if you want to print something on the screen from your signal handlers. So don't use printf inside signal handler. It's not safe. There's a bunch of other issues as well, not just reentrancy. These functions that are defined in cs.app.h, they actually use the read and write system calls to directly write on the screen on the standard file, standard IO input and output. And this type is similar to size t, but this S is for signed. So we have already seen size t. It guarantees the largest integer available on a specific system, 64 bits on 64-bit system, and 32 bits on 32-bit system. I told you this is C's attempt shot at portability. All right, so this is a lab question, but let's do some brainstorming. I won't really give the answer, but so what we are doing here is we are installing a signal handler, child handler. We are forking a bunch of children. The parent is spinning, and there is a problem here. Okay, very quickly, anyone, why does this seem to be a problem? When the handler runs, when the kernel delivers the sig child signal, the handler will run and reap there's a weight inside the handler, and the handler will reap the child, right? Why is this not correct? How many signals will the kernel deliver here? So if n is 5, how many signals? Think about it. Okay, we have discussed. Okay, hint. Implicit blocking. Implicit blocking. Yeah. I'm not using the guidelines. Yeah, okay. So my slides are not using the guidelines. Typical academic, it gives advice but doesn't follow it. Huh? Huh? The child blocks it? I don't know. So if the handler is running, you need to think about implicit blocking, right? And then it will probably lead to a good solution, or okay. So when the handler is running, if there is another signal, the kernel will not deliver it. That's how the pending signals work, and the signal handler will miss will never know that another child terminated. The solution is when you run the handler, you make sure you reap as many children as possible. Okay, you don't reap one child, you try to reap as many children as you can. Signals are blocked, but the kernel does have state somewhere about zombies in a table somewhere, and wait can still access that table. So when you're running a handler, make sure you reap as many children as possible. Okay, so there's portable signal handling. The problem is if you look at there were different versions of Linux have different semantics for signal handling. So some older systems, every time you run a handler, the main program needs to reinstall the handler. Some very slow system calls, blocking system calls like read, write, that access slow disk storage, they would actually never return. If they're interrupted by a signal handler, they would actually return with an error. So there is something called sig action that tries to clearly specify the signal handling semantics, or at least gives people the opportunity. So you can create this struct, and it really requires a user to set up the entries. So here we have a signal function that internally it is using sig action to set the handler to handler, and it is trying to give semantics, certain semantics for whenever we use signal. We don't have to use sig action. I just want you to know that there is something. And in cs.app.h and cs.app.c, they actually use sig action. So here it's telling the kernel to restart the system call on return and a bunch of other things. Okay. All right, so let's look at a couple of concurrency issues. So there is a problem here. This is also part of your lab exercise. So imagine that in the main program, we initialize a data structure that contains a list of all the jobs. Then we fork a child process to execute a specific job. Here we're just using the date instruction. This is, what is it doing? What is this sig proc mask doing? So sig fill set will include all the signals on the system in the block bit vector. So just like sig empty set, there is a sig fill set that fills the blocked signal vector with all ones. Okay, so all signals are blocked this way. So you have a mask all. Once again, look at the type, the previous all, and you install the child handler. You fork children, child processes, and here you are blocking all the signals and storing the existing mask in previous all, so you can restore the mask after you're done. Unblock all the signals. So this will unblock all the signals. So the parent, after forking the job, is adding the job's PID to a data structure. I'm not showing the whole code, just the function. And the child handler deletes the job. So the child handler blocks all the signals, unblock all the signals, deletes the job. So the flow is that the main program will create a job, add it to a data structure. The data structure I'm not showing, okay? And the child handler will delete the job. Whenever the kernel tells the process that the job, the child process has terminated, we need to delete the job from the list, right? Because we added the job when we forked the child. So what is the problem here? So the parent fork, add the job to a list, right? The parent is creating the job and adding it to a list. And the signal handler, the sig child signal handler, is deleting the job. It looks right, okay? When the job terminates, you delete it. And when you fork the job, you add it to the list, right? So what is the problem? There is a problem. At one point, a context switch will, okay, first of all, there is an interleaving of events that we are happy with. And that interleaving is this runs, then this happens. One should happen before two, okay? You should not delete something first and then add it. Cool. One should happen before two. Can two happen before one? That is my question. And we are touching concurrency. Concurrency will not come in one week. Here's a lecture on concurrency. It will be spread. Well, concurrency is part of our everyday life. So how can 2 happen before 1?
When expect really quickly and prove to people that before believing that part of.
Right. The in fact the temporal thing is not really important. It can run slowly or fast, but at whatever point. So if there's a context switch, if the signal is received at this point, what would happen? Right? If you fork the child process, if you're done with the job, there's only one CPU. This is a child process. This is process number 2. Let's call this process number 1. You agree? Process P1, process P2. P2 takes control of the kernel, has its own mind, right? Oh, I'm going to run the child. I don't care about the parent. Child starts running and it terminates at this point. Now, the pending bit vector in the kernel has a bit corresponding to sig child at this point, right? There is a signal pending, okay? So P and B has something, let's say 1, 0, 0. The kernel will say, oh, I'm returning from a context switch. Let me deliver the signal, right? While I'm at it, let me deliver the signal. It delivers the signal. The parent has the parent process installed the signal handler, and this starts running. And we delete the job before we add it. Okay? Welcome to concurrency. Now, what should we do about it? That's the question. Do we have all the tools we need to prevent us from? So this happens before is really a good tool for your reasoning. You want to take certain events and you want to make a, you want to figure out, reason which event will take place before another event. So if I want to prevent 2 from happening before 1, what should I do? What is the problem? The parent process here, can it do something to, what is the key problem? The key problem is that the signal handler runs. The key problem is that we have to stop the signal handler from running. Before what? Forget the context switch. Before adding the job, look at the data structures, look at the global variables. The thing that is messed up is the data structure in which you're adding something. Look at that, and that is your focal point. At this point, when I'm doing this critical thing, I want to make sure that only after I do this, the signal handler runs, right? But the signal handler could run at this point. If this is a program, the signal handler could run before this, right? Before this. So clearly I want to block sick child signal, but at what point should I block it? I want to block sick child before I'm sure that add job, I have added the job. So I want to block sick child, but at what point? Before forking. So I want to block sick child before forking. All right. Sorry, this is a corrected one. Oops, sorry. This is a, how did that happen? This is the, sorry, I must have pressed the wrong, but it's okay. The discussion was okay. So at this point, we block, we create a new mask, mask one, in which we empty it first, we add sick child, we install the handler, and we block it here. Now, why are we doing that? Why are we unblocking sick child here? Child processes inherit the block bit vector of the parent. Children inherit everything, the address space, everything. So we want to make sure we unblock sick child because the child process may want to receive those signals. So then we block all signals. So now we have ensured that we will not receive sick child until we are done with adding the job. So this will block sick child, and we store the previous bit vector in this variable, which we restore after we are done adding the job, and the child handler is protecting the delete job, once again, the data structure, by wrapping it around, blocking all the signals. So this is a corrected. Now, are there any, so race is between two events. When two events could take place at the same time, but we are only interested in a specific ordering of events. So that's when there's a race. And we need to do something special to prevent the race condition. There will be formal definitions of synchronization, races, and all that, but it's already, we can already see these problems in our programs. So here there's a race between add job and delete job. Anyone could run first. They are racing to run one before the other. And we have to make sure with what we did that add job happens before delete job. So this is called, synchronizing flows to avoid races. We have two concurrent flows, and we are synchronizing them so the correct thing actually happens. Okay, let's look at final thing with signals. Another example. So here, Okay, the correct answer to the shell exercise, we'll release it probably at the end of the week, and you have to use today's lecture to figure out what exactly to do. It's not that straightforward. I haven't given you the answer yet. So sometimes when you're writing shell and other utilities, what you can do is you fork a child, and you then wait in a while loop for the child to terminate. So what's happening here is you're forking a child process that will do something, but you set PID to 0. And then you are in a while one loop, and you will only come out of this loop if PID is greater than 0. Okay? So here you block these two. Sorry, here you block the child, and here you unblock the child. So here you block the child, and here you unblock the child. So when you unblock the child, you are inviting a sick child signal, right? And you're running a job, let's say. You will be doing something here. This is just showing exit, but you could be doing anything. In your signal handler, when you receive a sick child signal, you reap the child, and you set the wait PID function. Actually, the wait PID system call actually returns a PID of the PID of the child that you just reaped. And there's a property about process IDs. What is that property? Process IDs are always greater than 0. Okay? So when the child handler runs, process ID, PID, PID will be greater than 0. After the child handler returns, where do you go? You go back to the while loop here. And what will happen? You will exit the while loop. There is a problem. There is a problem. Now, this is a
PID global variable.
PID is a global variable. Yeah. So at this point, I want you to think beyond correctness. What kind of problems can we have beyond correctness? So correctness is one thing. So we are all. What is another problem? The way we write programs. Performance. So think about everything. What is this code wasting? It's burning the CPU, right? It's while one tuck processor is executing one instruction after the other, right? So this is a waste of time, waste of resource, but this will work correctly. You have a while one, you are checking the PID variable, and the signal handler will set PID greater than 0, and you will exit the while loop once you are done. This is a good way to reap the foreground jobs in a shell. There is something called pause. Pause system call suspends the process until a signal is received. Okay. But what is the problem with this? So this could be helpful to prevent waste, right? I can pause, and then when I get this PID greater than 0, I go out of the loop. Note that we still need a while loop here, because you might be interrupted by SIGINT. Okay, so there's a child handler for SIGINT as well. So you might get SIGINT. That's why you still need the while loop. Okay, but there is a problem. So you can think of pause as a sleep. The CPU is sleeping until there is a signal that is delivered, or the process is sleeping until a signal is delivered. So what's the problem with this while loop? After the while test, if you run the signal handler, what happens? If you run the signal handler after the while test, but before the pause system call,
I see issues that if the signal handler time goes between the while loop and the pause, it'll be waiting for like the next signal handler to call, not the one that is actually continuing.
if there's a more critical problem, if the signal handler runs after the while test, but before the pause, you're done. The process has been put to sleep forever. It will never wake up. So if the signal handler runs after the while test, where is our signal handler? It will read the process, the child process here. PID will be greater than 0. And when you return, you execute the next instruction, the next statement in program order. You execute pause. And at this point, there is no one to wake you up. You only wake up then when there's a signal, but the signal has already been delivered and you already run the handler. Now you might be tempted to do this. Sleep system call wakes up after, this is in seconds. So pause and sleep are useful system calls when you don't want to do something like this. And this is useful sometimes. We're writing systems programs. This while one is useful sometimes when we are waiting for, like in this program. The problem with sleep is that you never really know the granularity of your sleep. So 1 second, the processor can do a lot of work in 1 second. If you have a 1 gigahertz processor, how much work can it do? How many instructions can it potentially execute in 100 milliseconds? Okay, do the math. Assuming that 1 instruction takes 1 cycle, and each cycle is 1 nanosecond, that's 100 million instructions. That's a long time. That's a lot of waste from CPU's perspective. So we don't want to sleep for 1 second. So the solution is SIG suspend. SIG suspend makes sure that these 2 events, these 2 statements execute atomically as 1 unit. They cannot be interrupted. So we block all signals and we call pause atomically as 1 statement. How this is guaranteed by the kernel, this is not our concern, how it is implemented. So there cannot be a signal or an interrupt between these 2 statements. So when you call SIG suspend, you provide a mask. and you block all signals and you pause atomically. Okay. And this eliminates the potential race where this eliminates the potential race if these two statements are not atomic. So what we can do now is we can use SIG suspend in the while loop. Right? And when a signal is received and a handler runs, then SIG suspend actually restores the previous mask. Yeah. So you won't have a situation now where you're trying to block the signals and you already get a signal delivered and you run the handler and then you come back and you call pause. These two are uninterruptible, and this is somehow guaranteed by the kernel. If you have a okay, so you have a bunch of hints now for your lab exercises. And finish it this week. Now, I did have more stuff for today. I want to start with memory, but I think with the mess up at the beginning, I don't want to context switch. I don't want to context switch at this point with 5 minutes of a different topic, and we'll just start next week. Oh, sorry, on Thursday. Yeah. So these two cannot be interrupted. So you won't have, first of all, this cannot be interrupted, SIG proc mask. And there can't be a signal handler cannot run between these two. So
Could a signal run in like here?
That's a good question. Wait, but we are blocking we block SIG child here, right? I guess the problem with while it's a correctness problem here, right? So this is a correctness. Oh, sorry. This is a performance problem. So we're trying to fix a performance problem, not a correctness problem. So here we blocked sick child, right? So here we block sick child. So this is not a race condition. This is not a concurrency issue. So this is where we block sick child. Okay.
Yeah.
This is where we unblock it. So this is a correct program. And the problem is we are wasting too much CPU. Okay. So okay. We're talking about this one.
Yeah, so I guess there's an error if it runs here. Like if a signal's called here, right? If we use this instead of just like the colon. Like if you replace this one with a pause, would that cause a issue here? If like you had a pause here. Because of that issue you talked about before of saying like you could have a signal that happens before, like after the while and before the pause.
So if you have a pause here,
Like this race issue. So why does the race issue associate with this pause? not
because
also-
right, because so you block sick child, and you unblock. So we're assuming
We need a while ago. Just like
wait a second.
waiting.
Wait a second, we unblock it here. Sorry. We unblock here and we block here. So here we are open to receiving a. So you're asking why is if we put a pause here, that's a problem.
Um,
So you're saying if we replace it with sick suspend, why is it not a problem?
yeah. So like with the
they already do so.
Sick suspend. So let's say you have a while hit. And at this point, you, if you look at sick suspend, so at this point you could receive a sick child. Is it true?
Yeah.
You could receive a sick child here. If you look at sick suspend, if we look at six, so what we're doing here is, so you block the child, you're not unblocking the child, right? You're unblocking it here.
That's why.
So you unblock it here, and then this, you give previous, what is previous here? So previous is without sick block in the mask. So empty, sick child, okay? So, okay, sorry, I should have taken, so it's more complicated. Sick child is now part of the set. Now, at this point, you block sick child. Previous, if you install previous, you will unblock sick child here, right? Unblock it here. So this unblocks it and calls pause atomically, right? So you unblock. You unblock. So this will be unblocked in our case.
That's unblocking it. And is that
So
to
if you-
unblock it so that pause will actually work?
Right. So unblock and pause is atomic. So this requires an add pause. This is more than. So I was looking at my watch and how much time. So this unblock. If it's not atomic, then you unblock and you get a signal handler, and then when you return, there's a pause forever. Right? But by doing it atomically as one statement, you unblock and you make sure the signal handler does not run. You unblock and you pause. And if the signal arrives, then you run the handler, and then you come back and you do the 6 set mask to previous.
Okay, that makes sense. That makes sense.
And when we put temporary block it, because we have to unblock it as well.
Right.
Okay, so it's not going to, that 1 second is not going to be automatically expired.
Are you talking about this one?
No, 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 the example that you had, that we can
Ah.
temporarily for 1 second.
Yeah, this
we
one,
can-
this one.
Yeah, we get asleep for 1 second. After 1 second,
We wake
the
up.
kernel is not going to wake it up.
No, so the way sleep is implemented is you make use of the timer chip, the timer interrupt.
Yeah.
And after 1 second, the CPU gets a timer interrupt, and then it tells the kernel, and then the kernel tells the user process, hey, wake up, 1 second is up. And then you go back to wait.
Yeah, so we don't need to unblock it
Which unblock what?
for the signal handle. When we block it temporarily, or that's,
We're talking about signals, right?
yeah.
This slide does not have signal. That's why I'm confused. So can I go to this one?
Oh, yeah. So here, when we block it, we block it, we have to unblock it.
Yeah, that's right here. It's unblocked.
Oh, okay.
So this is a block.
Yeah.
You store the previous mask here, and then you use 6 set mask, apply the previous mask.
Okay. And in terms of that question that you asked, and I didn't dare to raise my
Yeah.
voice,
Yeah,
in terms of the children, because you said explicitly the kernel will not transfer it doesn't touch any integers.
the kernel blocks implicitly
Implicitly,
blocks
yeah.
signals
Yeah.
when a signal handler is running. Signals of
Yeah.
that type,
Yeah.
for which the signal handler is running, the signal blocks,
So the answer,
drops.
the answer of your question was 0 or 5. Or because you said
No, it depends, because when the signal handler is running,
Yeah.
the kernel can keep dropping all the signals that are being generated for that type.
sure. Okay.
Could be 0, could be 1, could be 2. Run in the lab and figure out.
Okay.
Yeah. You have a question?
Thank you very much. Thank you.
The 6 suspend. I think I will do an ad post because clearly it required more explanation than. But it's working.
I got a question about the PMB. So
Right.
when the PMB is like pending and not blocked. So when is this value calculated? It will
Whenever the kernel is returning from a context switch or an exception handler, because the kernel has the information about pending and block signals, and then when the user code is running, we don't do anything special.
yes,
To-
when the user code is running, we just directly go to it and
No, we don't go to it because we wait for the kernel to do something. When we make a system call,
reach it to it.
right.
So if we're in another process and this process receives signal and it would calculate the PMB when kernel calculate the PMB when it's context switching back and
These are policy matters. It really depends on what the kernel does.
Okay.
But we know the mechanism that so the distinction between mechanism and policy is very important in this course. So there is a mechanism whenever you're in the kernel has access to PNB, and the kernel may or may not decide to give it to you. We know that the kernel, so the mechanism is the kernel will notify the user process. Okay, this mechanism is in every operating system. Policy is when you do that. Okay. Different versions of Linux, Windows, Apple, Mac OS, they could differ in the policies. Some may decide you deliver the signal as soon as possible. Some may decide the next time you do a context switch from process A to process B, deliver the signal. It really depends. So policy is one thing, and we don't know the policies that are inside all the operating systems in the world. Mechanism is that here is a pending bit vector, and that informs the kernel that there are pending signals and they need to be delivered. When they are delivered, okay,
My question was about the re-entrant function.
Right. Reentrancy is complicated. Reentrant means that a function does not have any state beyond its execution. If it has, then things become more complicated. Because then, what if malloc has some state inside and a signal handler calls malloc? Okay. And signal handler has, it calls malloc. And now the signal handler is somehow depending on whatever the state of malloc is. And another signal, when malloc is called, another signal arrives when malloc is running. And that state is messed up. So when malloc returns to the actual signal handler, it is somehow the state is messed up. Okay, it's hard to explain. What could happen is if you have a function call and you call the function again, if everything is queried, we understand what re-entrant is, right?
End-to-end, yeah.
No, it means that all the variables are on the stack. And when the function returns, everything is automatically reclaimed. Like there is no state that exists beyond a function call. So signal handler, if the signal handler has static, it's a static variable. So imagine what could happen. So if you have a static variable and you call a signal handler, and then you remember that variable for some reason, let's say, but main program does something to that variable, right? And then the signal handler, whoever wrote the signal handler is not aware of.
So the signal
Wait a
handler
second,
main
this-
can actually still work concurrently. Like when a signal handler is running, main is still running.
They could run, wait a second, this example, this is a global, this is an example of a global variable. So when static, I'm thinking of an example where static actually is bad for signal handler. So if there's a signal, if there's a static variable inside the signal handler and you run the signal handler again, now you have state that is maintained across two calls to the signal handler, right?
Yeah.
And the reason it is bad is okay, I need to think about it. I'll think about it. I'm sorry, I'm too tired. Why don't we think about it? So what could happen? If you have state in your signal handler that is retained after the signal handler returns, when you run the signal handler again, actually, this is not about the signal handler. This is about the functions we can call that are reentrant. So if a function is not reentrant and we call it from the signal handler, let's say we call a function that has static variable. And that function receives a signal. I'm trying to think what could happen. So I need to think about it. But reentrant functions are, you can actually read the book as well. Reentrant functions are which do not have static variables. Everything is created on the stack. And so if you call a function that is not reentrant from a signal handler, then you need to know.
I might make an ad post about this.
What?
Like I might make a post ad about this.
Right.
To respond on there.
Right.
I have time to think.
Yeah. I'm not thinking properly.
So non-reentrant ones are where they do have internal state.
Right. But I cannot think of an example where just mess up the.
Yeah.
So what would happen? So what if you call a function that has static duration, variable static duration inside? The problem is your signal handler is running asynchronously, and when you call that function again, you are not sure what it will do probably. Because
it could have an unpredictable state.
right, because the guarantees you have about that function maybe difficult to reason about, but this was all advice. This wasn't like hard and fast rules.
Yeah.
You must do it. You can have static variables inside.
Are only like exceptions and signal handlers non-reactant, or can you make these functions non-reactant?
Signal handlers. You could have re-entrant, sorry, you could have non-re-entrant signal handlers if you know what you're doing. Right?
And
But
then,
it's surprise. I mean, it's kind of typically you use a signal handler to set a global state or something,
yeah, right.
but you don't really retain state across calls to signal handler. When do you use static variables? You use them when you are counting things and all that. But counting things inside signal handlers is dangerous because imagine you're counting the number of children. Each time a child terminates, you count how many children have terminated. This doesn't work, right? Because
Doesn't it?
no, because the kernel will not deliver the
Oh,
signal.
yeah. Because if it's right, if multiple come before it can.
Right.
that won't.
So it's kind of